Hi, this is Steve. Welcome to my class on complex analysis. Lesson number 1 is about complex numbers. We'll start with some motivation for why the complex numbers exist and follow that with some basic operations for adding, subtracting, multiplying, and dividing complex numbers. I'll give you a few examples and some exercises to work on. We'll do a little bit of graphing. It's pretty simple now when we're just talking about one complex number or a few at a time. And then we'll conclude with a challenge, which I think you'll find rather interesting. And we'll get back to that in a later lecture to actually explain how to solve that challenge. In terms of motivation, we start with the quadratic equation. We see that there at the top, ax squared plus bx plus c equals 0. That equation, as we remember from high school algebra, typically has real value solutions, or at least that's what you're exposed to in high school. And you can find those either through factoring the equation, and we see an example of that further down, x squared minus 3x plus 2. We can factor that as x minus 2, x minus 1, and then we see that the two solutions that give us a 0 value when plugged in are 1 or 2. The other option is, when you can't factor it, is to use the quadratic equation in the middle of the page, x equals minus b plus or minus b squared minus 4ac over 2a. And the square root sign is problematic if you have a negative number. And when you're first shown this in high school, you're normally told, well, there's no solution if you have a negative number in the square root. But that's not always the case, and in fact that's the motivation for complex numbers. Okay, and here we see the graph of the problem from the previous slide. It's just a quadratic that we factored. We saw the roots were 1 or 2, and visually it's a parabola, and the parabola intersects the x-axis, the horizontal line, at 2 points, 1 and 2, and that's the case where you have real roots. There's two other cases which we'll talk about in a second. Okay, so the additional two cases for a quadratic equation in terms of its roots are either a double root or a repeated root, and that's the first bullet item, x squared minus 2x plus 1 equals x minus 1 squared, and the root is x equals 1, and it's repeated. The parabola, if you graph it, it touches the x-axis just once at the point x equals 1, y equals 0. The other case, which is of interest to us, is when you have a negative number inside of the square root. So you see there x squared minus 3x plus 4. When you plug it into the quadratic formula, which I reproduced at the bottom left, you get 3 plus or minus the square root of 7 over 2. And you can rewrite that as 3/2 plus or minus the square root of minus 1. That's called an imaginary number times the square root of 7 over 2. Okay, and here we just have the graph of the quadratic equation that had imaginary roots. And it's visually pretty simple. It's just a parabola that doesn't touch the x-axis at all. And whenever that happens, you have only imaginary or complex roots. In general, for quadratic equations that have no real roots, there will be a square root of minus 1 term. We saw that in the example in the last slide. We used the symbol I to represent the square root of minus 1, noting that I squared equals minus 1. And this is pretty much the beginning of complex variables and then complex analysis. So for our example, previous example, we can, you see in the middle of the page there, we can rewrite that in terms of I, removing the square root of minus 1 and replacing it with I. This is typical notation. In general, complex numbers are of the form a plus bi, where a and b are real numbers and I is the square root of minus 1. And typically, and not just in this series of lectures, but in a lot of books, you'll see that the letter Z is used to represent complex numbers. So you see there we have Z equals A plus BI. That's just a notational thing. And if you have more than one, either you'll start doing Z sub 1, Z sub 2, subscripts, or if you just have a couple of complex numbers in an example, you'll typically use W. So that's just terminology that's kind of de facto standardized in various literature. So the set of all complex numbers are all numbers of the form, you see that at the bottom there, A plus BI, such that A and B are elements of the real numbers. And the double script C is used to represent the complex numbers, and the double script R represents the real numbers. This figure shows the complex plane. Every complex number can be represented as a point in the complex plane, and you see here we've represented various examples, like for example 1 plus I, it's the point 1, 1, where the first one represents the real part of the number, and the second coordinate represents the imaginary part, which is 1. We have another example there on the left, minus 3 plus 2I. So the minus 3 is the real part, and the 2I is the imaginary part, and it's 3 units to the left on the x-axis, and then 2 units up. So very similar to what we had for the xy plane of real numbers, but we now have the complex plane. So each complex number has 2 parts to it. That's important to remember. That'll cause complications when we get into limits and differentiation of complex functions, but that's for a future lecture. Okay, some exercises for the listeners to try. These are fairly easy. The idea is to find the solutions and then graph them on the complex plane that we saw in the previous example. So the first two, just to give you a hint, the first two are, the first one I should say has real solutions. The second one has imaginary solution, and then the two after that also have complex solutions. So go ahead and find those roots. I won't give you the actual answer, but I think it's pretty easy to work through those, just to give you a little bit of experience. Addition and subtraction of complex numbers is very straightforward. If you have two complex numbers, Z equals A plus IB and W equals C plus ID, you just add them term by term. You add the real parts and you get A plus C, and you add the imaginary part and you get B plus D, and it's the same thing for subtraction, except you just have a minus sign there. So we have one example for addition. If you have Z equals 2 plus 4I and W equals 3 plus I, then you add the real parts and you get 5, and you add the imaginary parts 4 and 1 and you get 5. And at the bottom of the slide we have an example of subtraction. So the real parts are subtracted, so it's 2 minus 4, and we get minus 2 for that, and then it's the minus 7, minus 5, and that gives us a minus 12. In this picture we have a graphical representation of the addition of the vector, or should I say the complex number 2 plus 4I and 3 plus 1 times I, or 3 plus I. And we represent them as vectors, and it's basically vector addition. So you can see here you create a parallelogram, and then the sum of Z plus W is 5, which is basically adding or going from the tail of 2, 4 vector Z or Z 2, 4 to n to the end, the arrow of the vector W, and you get 5, 5 is the sum. So that's something that helps occasionally. Normally you can just add them. You don't need to have the picture here, but sometimes it helps to see what it looks like in terms of vectors. Okay, multiplication is a little bit more complicated. We see here we have an example, or actually a formula, a plus bi times c plus di. And we're using the associative and distributive laws here. They're the same as what you would have for real numbers. They carry through. So you multiply the a times c plus di. I'm just reading across the line there. And then the bi times c plus di. And you multiply each one of those out and you get AC plus ADI plus BCI minus BD. And then you can just collect the real and imaginary parts and you get BC minus BD being the real part of the product, and then AD plus BC being the imaginary part of the product. And we have a simple example here, 3 minus I times minus 1 plus 2I. So we can either use the formula or you can just manually go through it. You have the 3 times the minus 1, it gives us a minus 3. And then the minus I times 2I, we get a 2 because I times I is minus 1, so that negates the negative. You get a 2 there. And then you multiply the minus I times minus 1, that gives you a 1 times I. And then the 3 times the 2I, and you get a 6. And then you add those together, the real and imaginary parts individually, and you get minus 1 plus 7I. All right, so you might want to try that. I left a couple of examples for you, or exercises, I should say, at the bottom. You might want to give those a try just to get used to doing that. The complex conjugate of a complex number just changes the sign of the imaginary part. So you see, if we have z equals a plus bi, then the conjugate is a minus bi. On the right, we have an example. 1 plus 3i has conjugate 1 minus 3i and vice versa. And it's always the case that the conjugate of a complex number is the reflection of that number about the x-axis, which you can see from this one example. Taking division of one complex number into another is a little bit more involved. You see there on the first equation on the page, we have a plus bi divided by c plus di. The way to solve that is to multiply by c minus di divided by c minus di, which is just 1. But the advantage of doing that is in the denominator you get a real number, c squared plus d squared. And in the numerator you get a complex number using the procedure we did for multiplication. And taking an inverse is sort of a special case of division. So if you had z equals a plus bi, then its inverse, just looking a little further down the page, is 1 divided by a plus bi, but the 1 is really 1 plus 0 times I. So it's a special case of the division. And working through that, you get the inverse is a minus bi divided by a squared plus b squared. So if we took 3 plus 4i and we use the procedure above, or the formula above, the inverse would be 3 minus 4i divided by 25. And we can check that out by actually multiplying 3 plus 4i times 3 minus 4i over 25. We can take the 1 over 25 out and then multiply the 3 plus 4i times 3 minus 4i, and you see there we get 9 plus 16 is the real part, 12 minus 12 is the imaginary part, that's 0 of course, and then we just have 25 divided by 25, and that equals 1, which is what you expect when you multiply a number times its inverse, or at least its multiplicative inverse. You get 1. Okay, a few examples or exercises for you to try. Take the inverse of 1 plus I, and take the inverse of 2 minus 3i. Then the second two examples are basically division, so do the long division that we described in the previous slide and compute your answer. And I did give you the final results, but not the steps involved, so hopefully that'll help you to verify that you've done it correctly. Okay, we have a challenge here on the last part of our lecture. This is quite difficult, and you may not have seen this, even if you've had a little bit of experience with complex numbers. This may be new to you. The wrinkle here is that the quadratic we have, some of the coefficients are complex numbers. And just putting these into the quadratic equation is not going to give you an easy way to the solution. There's some complications involved here. So I did give you the final answer, and we'll come back to this later and explain uh, how to make this work. But you might want to struggle with it a little bit just to get some appreciation for the difficulty or the variation when you start adding complex coefficients to even a simple equation of the second degree.